Okay, folks, this is our first big lesson in the rotation unit, and we're talking about, we're moving on from kinematics. So we have our rotational motion demonstrator here, and you can see like the top of it, and that's what you've been used to seeing. What I want you to focus on is not what's on top, but what is just beneath the surface. And so I want to draw your attention to this wheel right here. So this is a motor, it's spinning an axle, and there's a wheel here with like a rubber O-ring. So it looks like a hair tie, but it's made of rubber, so it's a lot more grippy. And it's spinning, and it is causing the platform to rotate. Now there's a pulley here with its own O-ring, and that's mostly just for balance, because the motor can only be on one side at a time. So it actually rotates by pushing the platform in this direction. Now I want to show you something that I can change with this. So I'm gonna stop this, and I'm gonna change something. So this wheel can be moved. I'm gonna move it way in here, and start it up, and we'll see if I can get it to move. And actually it's doing what I want you to see. Even if I spin it, it doesn't continue to move. The motor is actually not strong enough to move this. So the motor causes that wheel to apply a specific force. Now if I move it out a little bit and restart it, you can see that it actually does start moving, and it is accelerating. Mostly the way you'd be able to eyeball that is that it's getting a little louder, but you probably can't hear that. So what happens if I move it all the way out? The motor is still applying the same force, but the result is I get this much more dramatic acceleration. And so this has to do with today's topic, and that topic is torque. Stopped, and let's write down some stuff. So camera is moving. And there we go. All right, so there it is. So torque, the measure of how much a force acting on an object would change its rotational motion. So just because there is a torque doesn't mean that the rotational motion of an object is going to change. Torque more describes the relative ability for a force to do that. And so if we'd like to think about the rotating platform, the motor allows that wheel to apply a constant force. The torque doesn't, or the force doesn't always result in the same motion of the object. And so you noticed as I moved the wheel further away from the axis of rotation, the platform rotated faster. And so we have, in addition to force, we have an additional variable that's important, and it's the one that you've been familiar with ever since we started rotation. It's the value of r, in other words, the distance between the force and the center of the axis of rotation. So as far as the equation, the torque equation looks like this. So we have this funky looking letter, which is the Greek letter tau. That is the variable for torque. In your equation sheet, the equation for torque is reported as R parallel F, which is equal to RF sine theta. So what does that mean? That is the force times distance from axis times the sine of the angle between them. So force is pretty easy to understand. Any force can exert a torque. And so the force is just like any other force we've studied. The R is how far is that force from the axis of rotation, and then this is the weirdest part, sine theta is the sine of the angle between them. So the way that I usually explain this in class is with a door. So here's my version of a door, and here are the hinges. And I'm going to draw them pretty like vague, but those are hinges. And so, you know, we look at the door in the classroom and we think like, oh, the doorknob is over there. Why do they put doorknobs all the way over there? And so very quickly you could see, based on this torque equation, that this is just about the maximum value of R you could have for the door. The door rotates around the hinges, which are the axis of rotation, and so if you put the doorknob as far away as possible, it will maximize the torque. Okay, so this is the front view. Let's look at the top view. So here's the door itself. Here are the hinges. And then here's the doorknob. And so what happens? Well, you go up to a door, you grab it by the doorknob, so here's the point where you apply a force, and you push straight through, and that applies the force. So the force gets exerted like this. And so as far as the torque equation is concerned, we make the following analysis. The hinges are right here. The distance that the force is away from the axis is going to be measured like that. So it actually, the R gets measured through the object in the way that we're going to analyze it. When you go take physics in college, you will learn about things like the moment arm or the lever arm or the line of action. We can simplify things a little bit in high school and just deal with, okay, if we imagine that R goes directly through the object and the force is applied in whatever direction it's applied, we can determine the angle. And so the angle, in this case, is 90 degrees. So for using a doorknob the way it's intended, the torque is going to be RF sine of 90 degrees. And so if we haven't talked about it yet, yes, I'm using degrees, and we've been talking about radians the whole time, and that's frustrating. And so we use radians to describe the rotational kinematics of something, but if we're actually measuring an angle between other vectors, we can use degrees. So the trig is always going to be with degrees for us. So back to this, RF sine 90, which means it's just equal to RF, because the sine of 90 degrees is 1, and so we get just RF. So we have this concept that happens outside of the AP exam, that when you make your force at a 90-degree angle from the object you're trying to rotate, that maximizes its effectiveness. And so if you imagine, like, what are all the wrong ways to open a door? Well, if you go up to a door, you grab it by the doorknob and you push this way on the doorknob, it's possible that the door might open. But if I if I want an angle, if I move this vector up so that it's parallel to that, to the original, and it's also connected now to the radius, this is a pretty big angle. Now, the sine function, if you go from 90 degrees to greater angles, let's say this is like 135 degrees. Of course, I don't have my calculator, so I can't give you a number. The sine of 135 degrees is 0.7. So if I use the doorknob and pushed at this bizarre angle, like out toward the, like away from the door almost, I get this bigger angle. The sine of 90 degrees is 1. The sine of 135 is 0.7. So I only get 70% of the torque if I use that angle. And so that angle is really, really important. So again, we come back to these variables. The amount of torque that you can deliver depends on the magnitude of the force, the distance that force acts away from the axis of rotation, and the angle between the radial line and the force. And so we will talk about all sorts of examples, but the doorknob is just one of them. And so just, to give you some pictures here, if you're trying to rotate something, if this is like a diving board and you are standing on the diving board, well then your value of R is going to be here, it goes right along the diving board. And then your body has a certain weight, and so you are applying that force there, and this is a 90-degree angle. And so the torque in this situation is going to be R times mg times the sine of 90 degrees. And so that's like, a pretty clear-cut example where you're standing on something. The hinge of the diving board is here. Now, yeah, diving boards, unless it's like a high dive, so we'll imagine it's a high dive. It's a high dive diving board. And so we'll imagine that it's a very simplified anchor here that's holding it up. And so it's a rigid, like regular diving boards are pliable, the high dive ones are not. So that's the torque equation will play out like that. Now, let's imagine okay, this is going to be kind of goofy. So you're standing here, and one arm's out like this, and the other arm's out like this. You have really long arms for your height, and that's okay. And you are holding on to a rope, and that rope is being pulled in the other direction. Or maybe someone just comes up and grabs you by the arm and pulls you. So they pull you with this force. And so thinking about there's a couple things that are going to happen, but your arm rotates around that axis right there. So if I'm thinking about okay, is this force going to cause a torque on my arm? So the R would be measured there from your shoulder to your hand, and then the force would be delivered that way, and then this angle pretty much looks to me like 180 degrees. And so as far as the torque on your arm, it would be R times F times the sine of 180 degrees. Well, the sine of 180 degrees is 0. So the force here has no hope of rotating your arm because the force is directed along the radial line of your arm, and will not have a chance at applying a torque to it. On the other hand, your body itself can rotate because you're standing on the ground. You could alternatively measure a value of R that way. And, if the force is strong enough, this force can make you leave your feet. It can cause your body to tip over like that, pulling the top of you while leaving your feet where they were. Your body essentially rotates like that, and it could rotate. So those are, kind of the big ways that torque applies. It's important to note that sine has a maximum at 90 degrees and a minimum at 0 and 180 degrees. Last thing, units. I saved this for last because it's uncomfortable for some people. It's radius times force times sine theta. So theta doesn't have units, but radius and force do. The units of torque are Newton meters. And why is this uncomfortable? Because if you remember, work has the same units. These are crazily not the same units as work or energy. That is a conversation for your college physics professor to start and finish with you, but basically it has to do with the fact that this method of multiplying vectors is not the same as the way we multiplied them with work. And so the high school version I can give you is when we calculate work, we do FD cosine theta. When we do torque, we do RF sine theta. The way that physics plays out and math plays out, this method of multiplying vectors gets a different result than this one. The result of this is a scalar quantity, and the result of this is a vector quantity. So torque is itself a vector that will cause a specific change in rotation. So the unit's Newton meter. It depends on which concept you're focusing on. If it's energy and work, then it's Newton meters that are the same thing as joules. But if it's torque, Newton's meters are not torques. Are not joules. And that's it.